Hey everybody, it's Ripley back again. We're going to talk about exponential growth and decay. I realized that this is a topic that is typically covered in your Algebra 2 or maybe even in your, in your pre-calculus course, but we're going to bring it up again here for a couple of reasons. We're going to talk about it because it's a nice little introduction to differential equations, which can typically be covered really anywhere in a given text. Okay, but it's kind of important that we discuss it, and it's kind of we're right here, we're starting to get into applications of derivatives, so this seems like a decent place to start talking about some theoretical explanations about derivatives. All right, so exponential growth and decay. I'm going to come at it from a way that you may or may not have seen before in the past. Yeah, what we're going to do is, this is not going to take long. You've already seen this. I don't want to waste your time. But I'm gonna come at it in a different way, like I said. What I'm going to do is I'm going to write what's called a differential equation. And we'll talk about differential equations down the road because they have some very interesting properties. This thing's called a differential equation, or a diff-EQ, as opposed to a def-EQ. What? Sorry, I couldn't resist. A diff-EQ, I know that's not the way it's spelled, guys. A differential equation is an equation with an unknown function and at least one of its derivatives. So my unknown function, now remember your rules. This is my dependent variable. This is my independent variable. So my function, this unknown function, is p of t, or just p. All right, but when I'm done, I need to have a function of t. Okay? All right, so a couple things. First things first. We will, down the road, we will show that the solution to this differential equation is actually p of t is equal to p naught e to the kt. Hey, you've seen this before, right? This is the exponential growth and decay function. This guy right here is called the relative growth rate. Relative growth rate. All right? That's what that bad boy is right there. Now, it's called the relative growth rate because if I solve for it here, watch this. Do you agree that I will get k equals dp over dt divided by p? So let's sort of parse this out in English. dp over dt is the rate of change of, if we're talking about a population of, I don't know, of bacteria in agarose, right? The rate of change of the population at any given time divided by the population at that time. So this is the growth rate, but as soon as I divide and make it relative to the amount that was there at the time that I measured the growth rate, that becomes the relative growth rate, which makes sense. It's the growth rate relative to the amount that was there initially. Okay? Now, I am not going to waste your time going through problems like this. You can either do that with your instructor or you remember how to do it, and it shouldn't be a big deal for you to know what to do with that. Just remember this. If k, so from here, let's change colors. I don't like this. It's hard to see what's going on. Let's come over this way. If k is greater than 0, this implies growth. Most commonly, we talk about it with like bacteria in a petri dish, something like this. If k is less than 0, this implies decay. We talk about this, excuse me, with like radioactive decay. You've seen this before, all right? Don't panic. You'll be fine, all right? You've seen it before. Another ramification, this is kind of fun. Again, this, I know it feels like a side note, and it kind of is, but don't fret. It's kind of a fun little place to stop and take a break. You've been taking a bunch of heavy-duty derivatives. Now look at this. I don't like this notation, but it's in every textbook that I've ever seen. And this is Newton's law of cooling. So this has to do with exponential decay. All right, decay of a temperature. This is k times t minus t sub s. Now I want to take a minute here and make sure that we understand what these mean in English terms. This little differential equation, what it's saying is the rate of change of p as a function of t is proportional. That's a constant of proportionality, even though we know it's a relative growth rate. It's proportional to the amount that is present. This says, this is Newton's law of cooling. You've seen this before, right? Newton's law of cooling. So in other words, you take a pizza out of the oven, you set it on the countertop. The rate of decay can be described by this differential equation. It says the rate of change of temperature is proportional to the difference between the temperature of the pizza and the surrounding room at any time. It's always proportional. Okay? Now, what this always solves to be, excuse me, what this always turns out to be is I get T as a function of T is equal to the temperature of the surrounding plus, now this is where it gets a little bit tricky. We're going to have what we've got is we've got T initial minus T surrounding, because I'm cooling, and this is going to be E to the KT. This is the formula that you've seen. This is the formula that you'll always see in like your Algebra 2 textbook. They just give it to you. We can down the road, once we start solving differential equations, we can come up with this equation on our own. It doesn't have to be force-fed to us. Right now, we don't have the calculus wherewithal to be able to do that yet. All right? So this is a super common formula that shows up. There's not a whole lot to it. It's pretty easy. Okay? All right, pretty easy to work. Again, I'm not going to insult you by doing a bunch of examples. Last but not least is the compounding continuously compounding formula. And then I'm done. Compounding formula. Here it is. Okay, and this thing comes from, I know that the amount of money, think of money, all right? The amount of money is always equal to the principal. Again, I know that you've seen this before, so don't freak out. Times 1 plus R over N to the NT. Now, I will tell you what this is. What this says is if you take a principal is an initial amount of money, and you stick it in an account, the amount that money will be worth after some time T is equal to the principal times 1 plus the rate of interest, written in a decimal form, not a percentage. This is always a decimal. N is the number of compounds per year. It doesn't matter how long the money is in the account. If the amount is in the account for 1 second and it compounds weekly, then N is going to be 52. If the amount is in the bank account for 3 months, but it compounds daily, then N is going to be 365. And then this is kind of cool. For this equation, T is always in years. In these equations, T doesn't necessarily have to be in years. It could be in minutes, it could be in hours, it could be in seconds. But for compounding, this always is in years, always. Now, an equation that pops up as a result of this, if continuously compounding means that you're basically taking infinitesimally small slices of interest and adding it to the principal. Now you may be, Ripley, wow, how does it not blow up into billions of dollars? Well, because they're really small chunks of time. They're infinitesimally small. So what I can say is that the amount as a function of T is going to be the limit as N goes to infinity of P times 1 plus R over N to the NT. Now, again, I won't go through the algebra. Maybe you can do it with your instructor, because this is more of an algebraic exercise than it is a calculus exercise. But know that this turns into P e to the RT. So the amount, I'm going to get rid of this A of T, and I'm going to call it P of T. Well, no, let's leave it as A of T. Let's leave it as A of T. I know if I let the number of compounds blow up and go to infinity, then A of T is equal to the principal, the initial amount. Hey, that looks kind of interesting. That's an initial amount right there. E, that's E. R is the interest rate that you're collecting, and T is time in years. Kids, that's it. That's it. You've already seen these. So enjoy the little respite from calculus and have some fun with it. Most textbooks, most calculus texts, when they start talking about exponential growth and decay, you're still going to have to answer questions about derivatives, but it's a nice little review and a nice little break. Okay, enough. Stop yapping, Ripley. I'll see you guys in the next section.